I hope your takeaway from the last few days has been that a derivative is a function that tells us the slope of the original function at any point. So derivative, slope, that's the connection you want to make. If we're going to spend the whole, pretty much the rest of first semester, finding derivatives of functions and then using those derivatives to solve problems, we want to make sure before we step off of a cliff that we know a function has a derivative before we go trying to find one. And in cases where we don't remember to check that a function is differentiable, meaning it has a derivative, then sometimes we can accidentally find a derivative when one doesn't really exist. So it's going to be our responsibility to check. So there are 4 ways that we'll talk about right now that a function might fail to have a derivative. Remember, derivative is slope, and we said that a derivative has a limit definition. So the limit is h approaches 0 of f of x plus h minus f of x all over h. And remember from chapter 2 that a limit doesn't exist at a certain point if the limit from the left and the limit from the right don't match. So similarly, the derivative doesn't exist at a certain point if the derivative from the left and the derivative from the right don't match. So here's one way that could happen. If you think about the absolute value function, it has a corner, right? When you think about the graph. So any sharp point like that, sharp turn on a graph, we call a corner. And here's what's happening. So that's what you're probably going to memorize. Oh, no derivative at a corner. That's fine. That totally works. But why is there no derivative here at this corner? Because look, as I approach x equals 0 from the left, what's the slope? What's the derivative? Well, it's going downhill. So even if you don't know that it's -1, you know the derivative must be negative because the slope is negative. Here, as I approach x equals 0 from the right, if I look at the slope of that part of the graph that's to the right of x equals 0, the slope is positive. So I know my negative slope can't equal my positive slope. I have 2 different derivatives. That's why the derivative will fail to exist at a corner. A cusp we don't see too frequently. It happens when you raise x to a fraction power and the numerator is even and the denominator is odd. So similar to a corner, you can tell that if I tried to figure out the slope coming from the left, it would be negative. If I tried to figure out the slope coming toward x from the right, it would be positive. My derivative will fail to exist at a cusp. Here, this is the graph of the cube root of x. What's going on here? Remember, derivative means slope. And what's the slope of a vertical line? It doesn't exist. So if you have a place on your graph where you try to draw in the tangent line and the tangent line ends up being vertical, well, that means the slope of your curve is undefined because the slope of that vertical tangent line is undefined. So let me make my point here. Whenever your graph has a vertical tangent, there will be no derivative at that point. And here, this is sort of like an informal definition if you're at Starbucks and somebody asks, hey, when is a function differentiable? This is probably what you'll say. It has to be smooth and it has to be continuous. But I want to be really clear that if we look at this graph, that looks pretty smooth and it's definitely continuous. So notice that this sort of summary statement, smooth and continuous, doesn't specifically call out the existence of a vertical tangent. So that one you're going to have to remember. We can use our formal definition of differentiability, which we'll get in a second. But this list of 4 things is probably what you're going to want to keep in your mind. You want to look for corners, cusps, vertical tangents, and anywhere there's a discontinuity. Okay, so this last one. This is important because before you can even talk about whether the slope from the left equals the slope from the right, you're going to have to check that your function is continuous, at least at the interesting x value, at least at the one place where you're interested in the derivative. So I'll just point out that as I approach x equals 0 from the left, the slope was 0. And as I approach x equals 0 from the right, this is another horizontal line, the slope is also 0. So here's my 2 slopes, my 2 derivatives match. But none of that matters if my function is not continuous at the x value I'm interested in finding the derivative of. So a function is not differentiable at any place where it has a discontinuity. And I can I can tell you that now that I think about it, maybe that one should go first, because you're going to want to check for continuity before you even worry about checking for any of those other things. All right, most of the functions we're going to study are differentiable, but that doesn't get you off the hook from having to check every single time that your function is going to be differentiable before you try to take the derivative. There are plenty of places, and they might even specifically, purposefully try to trick you into taking the derivative of a function, and you'd be able to find a derivative if you didn't stop and remember, oh, not actually differentiable. So there's a question on your paper. What's the function, one function from your function booklet that has a point in its domain at which it's not differentiable? So there's one answer, but that doesn't include any of your, remember when you got to make up your own you got to include a function of your own choosing. So you're going to have to leave that one off the table because I don't know what you picked. So of all the functions that everybody put in their book, there's one that has a point in its domain at which it is not differentiable. See if you can name it. Okay, some of you, when you were working on your 3-1 notes, you noticed that there was another definition in your book. They called it an alternative definition for the derivative, which is different from the alternative we wrote in. So here it is now. All three versions of the definition of the derivative are going to be interesting and important to us this year. So make sure you find a chance to get to know them all. If you want to write them all in on your important facts paper, you might like to have them there. Notice the original one, the limit as h approaches 0 of f of x plus h minus f of x all over h. That's the one definition that gives us out a function of x. So f prime, a function of x. The other two, so the one that we copied down in 3.1 plus this one, they are, I can see there's a typo in my slide already. They are definitions for f prime at one single point, specifically a. So that, where it said f prime of x in my slide, should have said f prime of a. So this expression can give us derivative at one single x value. Okay, and they're all going to be important to us. This one is new to us today, and it's going to help us write our specific formal definition of differentiability. So a function f of x is differentiable at the point where x equals a, if and only if two things. Number one, it has to be continuous there. It's going to be your job to check before you try taking the derivative. And the limit as x approaches a from the left of f of x minus f of a over x minus a has to equal the limit as x approaches a from the right of f of x minus f of a over x minus a. So I'm hoping you will recognize this expression as the derivative, that new alternate form that we just wrote down a second ago, and that it's, now we're comparing the derivative from the left has to equal the derivative from the right. Okay, so that part we knew already from our beginning section. This is the formal way to say that a function is only differentiable if its derivative from the left is equal to its derivative from the right. So slope from the left has to equal slope from the right. So there's a place for this in your 3.2 notes paper, and there's a place for this on your important facts paper. Make sure it gets there. Alright, so two quick theorems. This one, nobody's going to really test you on it like a theorem, but you're going to be surprised how convenient it is to remember this whenever possible. So, a function must be continuous to be differentiable, which means if you ever find a function that you know has a derivative, it must have been continuous. Otherwise, you wouldn't have been able to take the derivative in the first place, right? So if a function has a derivative at a specific x value, then it must also be continuous at that x value. Here's another quick idea. It can help you save a step sometimes. I've never seen anybody actually get tested specifically on this. Nobody's going to ask you about the intermediate value theorem for derivatives. But since a derivative, let's call it f prime of x, is a function, it must follow all the rules for functions. So if we know that f prime is continuous, then it must follow all the rules for the intermediate value theorem. So if a and b are any points on a function f, and we know f is differentiable, then f prime is going to be continuous, and therefore between the slope at A and the slope at B, the derivative must take on all the slopes in between.